Hello everyone, and welcome to the Hidden Truths, a place where we explore scenarios, histories, and truths normally hidden from the public view. Not so much this time. Big thanks to Cirnosad for compiling this. I'm going to get you up to speed with the basics of atomic physics. If you already understand the words chain reaction, mass defect, and fission, you can skip this course. Everyone else, let's go! As you all know, we are made of bundles of atoms and energy. If you ignore a lot of the Schizo standard model crap, there's just 4 basic ingredients. Only 3 in some models, but we'll get to that in the future. Electrons, photons, and protons and neutrons. Electrons and protons are charged particles that attract each other and are repelled by themselves. An atom is made up of a positively charged nucleus and a cloud of negatively charged electrons. Photons mediate energy transitions for both the nucleus and the electron cloud. Inside the electron cloud, chemistry happens. Conventional explosions activate through transformation from one molecule, a collection of atoms, to another, generating heat, photons, and momentum in the process. That energy activates more reactions. This is called a chain reaction. To state another way, exothermic reactions have 2 sides. The reactant plus activator equals products and energy. In the special case, when the product of a reaction is also an activator, you get a chain reaction, since the reaction can continue until we're out of available reactants. These conventional explosives will move the nucleus around a bit, but won't make it undergo a reaction of its own. There's a good reason for this. It's a huge energy required, except during low energy nuclear reactions. We'll look at that later. Let's look first at the scale of energies involved in chemical reactions. The energy it takes to strip an electron from a hydrogen atom, which is simply a proton nucleus that has an electron spinning around it, is around 13.6 electron volts. That is around 1.3 megajoules per mole. This is a huge amount of energy given a mole of hydrogen is about a gram. But nuclear reactions are on a totally different level. To understand why, we have to enter the mass energy equivalence. Poincare, not Einstein, proposed the following mass energy relationship: E equals m0 c squared. He derived this using Lorenz's transformations in self-interacting fields. What does this mean in practice? It means that the mass of the nucleus, and indeed electrons, can get involved in the reactions and produce energy. In short, by measuring the weight of the products and reactants, we can calculate the resultant energy. Let's take a look at one example. It is said that the currently modeled neutron decays into an electron and proton when isolated from the nucleus of an atom. How much energy is released? For reference, the energy equivalent of our particles follows. The proton has 938.28 million electron volts. The neutron has 939.57 million electron volts. And the measly electron has 0.511 million electron volts. Thus, remember our equation is mass defect equals reactant minus product, which is 939.6 minus parentheses 938.3 plus 0.511 equals 0.78 million electron volts. That's more than 58,000 times the energy it takes to strip an electron from a hydrogen atom. We see this nuclear reaction is 4 to 5 orders of magnitude larger than chemical reactions. Note, for the nitpickers, the electron stripping from a hydrogen example is in fact much larger than the energy released by chemical reactions that can undergo a chain reaction. Explosives, so it is a sufficient example for our intentions. Another slight detour. As it happens, these large numbers are really inconvenient for lazy bakas, and we like to use atomic units based on carbon-12, which is what you're made of. Which is, the proton is 1.007276 units. The neutron is 1.008664 units. And the measly electron is once again 0.000548558 units. Very, very small, very teeny. Now let's move on to something more explosive. Fission! What is fission? Fission is when an unstable atom splits into smaller atoms and releases various other stuff, mostly neutrons and lots of energy. Photons. Why are atoms unstable is sort of an open question. Some atomic configurations, isotopes, just don't like existing. Take uranium-236 for example. This is one annoyingly grumpy molecule. Give it a long enough time and it'll split into two atoms, called daughters. Get it? While producing a lot of energy and 2 or 3 neutrons. The energy released is immense, but depends on what products are made as per the mass effect. How do we exploit this? If we want the juicy energy produced out of it, let's knock on the door of its thinner brother, uranium-235. This one has 1 less neutron than U-236. So what if a slow neutron were to visit U-235, get swallowed up by it? It'll turn into a very grumpy U-236. It gets very deformed. This will undergo fission almost immediately. Notice that the products include an activator, a neutron. A massive chain reaction is possible. So let's do some math on one example of our grumpster, creating 2 barium-141s and krypton-92 daughters. Uranium-236 to beryllium-141 plus krypton-92 plus 3 neutrons. The atomic weights balance out, but the energy produced by fission is many times greater than the energy produced by spontaneous neutron decay. Aside, we cannot have a proton visit U-235, since it will be repelled by the positively charged nucleus. Also, moral might needs to be slow later, and the origin of the binding energy associated with an atom versus its individual particles is an open problem. Uranium-236 is 236.04556 units. Beryllium-141 is 140.91441 units. And Krypton-92 is 91.92615. And the 3 neutrons are 1.00866 each. Thus, the mass defect, when you do the math, 236.045568 minus the rest of the molecules, 140.91441 plus 91.92615 plus 3 times 1.008664 equals 0.179009 units. This is equivalent to 166 million electron volts, 200 times greater and more energetic than the spontaneous neutron decay. This means that such a reaction per unit is more than 10 million times more powerful than a chemical reaction. This is why the Manhattan Project was formed. You see, conceptualizing this reaction and doing the math is easy, but turning it into a weapon, that's an art form. So how do we go about turning the fission idea into a weapon? Do we do away with our chemistry set altogether, or will chemical explosives come in handy? Where are we going to find these neutrons that keep decaying on us? Find out next time on Physics 002. Thanks for watching. Hope you all enjoy. Bye-bye.